Now, we've already looked at what's the potential energy of a charge in a constant electric field. We're now going to move on and we're going to try and develop the potential energy between any two-point charge. So in our system, we have two-point charges, Q and QO. We're going to fix Q at a distance of r equals 0. We're going to place QO at r equals A. We're going to move QO to r equals B. We're going to follow the same steps we did before to find the potential energy. So our axis refers to the r direction, and we pick r because in our Coulomb's equation for force, we call r the distance between the charges. So we're going to call our axis r, and our charge QO moves from point A to point B. So there's the path QO moves along. Let's start by writing down the expression for our work. We know that the work done on our charge QO is the integral from A to B of the force over the distance. Now, our charge moves in the r direction, so I'll call my distance r, dr. That's a scalar product, so I've got the integral from A to B of F, so the magnitude of the force, times the magnitude of the displacement, times cosine theta. So dr, remember in our math terms, it's a little bit of our path. So there's our dr. Okay, so now let's just pause and think about the sign of our work done. And that's pretty important to remember because we want to make sure we have the signs correct. So I didn't specify the signs of my charges, and the signs of the charges can be anything. Well, I suppose not anything. They can only be positive or negative. So if my two charges are positive, that means that my force on QO is going to be repulsive. So QO will be repelled by Q. So if they're both positive, it's going to be a repulsive force. That means that my force is parallel to dr. And if my force is parallel to dr, the work is going to be positive. Okay, that's one situation. Turns out we get the same thing if they were both negative. We'd still have a repulsive force. My F would still be parallel to dr, and my work would still be positive. Okay. So what if my charges were opposite? So either Q is positive, QO is negative, or Q is negative and QO is positive. Then my force is attractive. So then the force on QO would be towards Q, but my dr would be away from Q. So those would be in opposite directions or anti-parallel. So F would be anti-parallel to dr, and my work would be negative. Okay, so that's kind of important to establish. And now the other thing we know that we can think about is that the force between my two charges is the Coulomb force. So my force is equal to K times Q times QO divided by the distance between them squared. So whatever that distance is. So if we write our expression for our work is equal to K times Q times QO over R squared times dr. So what I've done here was I substituted in my Coulomb's law for my force, and I left out my cos theta. Okay, there's a good reason I left out the cos theta. The cosine theta here in our expression for work takes care of the sign of the work. If the two signs of the charge are the same, my work is positive. Okay, let's think about that down here. If my two charges are positive, my work is positive. If my two charges are negative, my work is positive. If my two charges are opposite, then cosine theta is cosine 180 and my work is negative. If my two charges are opposite here, one is plus and one is minus, then my work is negative. So these two expressions give us the same sign for the work. These two expressions are equivalent. So I'm going to work with this expression right here because it's a little easier to deal with because now I don't have to put in different values of theta. I just have to put in the signs of the charge. So I think this is worthy of a note right here. Include sign of charge to get the correct work. Okay, so now we have the work all well established. Next, we want to figure out what is the potential energy. So we know the change in potential energy is related to the work. I'm not going to try and squeeze this in this slide. Let's go to the next slide. To carry on now, let's remember where we're going with this. We know that the change in electric potential energy is the negative of the work done. So before we move on to write out what is delta U, let's go ahead and finish our integral here so that we get a finished expression for the work. So our work is the integral from a to b of kq qo over r squared dr. We can take our constants out front of the integral. So k is a constant, q is a constant, qo is a constant. Doing the integral from a to b, 1 over r squared dr. This integral form should be pretty familiar from your math class. The answer to that integral is minus 1 over r. And that's going to be evaluated at points A and B. So that's minus kq times qo outside of 1 over r at point B minus 1 over r at point A. So here's our expression for our work done. And now we know that the change in electric potential energy is the negative of this expression. So delta U equals minus work equals plus K times Q times QO times 1 over RB minus 1 over RA. Okay, let's move on to the next step of this expression. And let's just remind ourselves of what does delta U mean. So let's put an and symbol in here. And delta U is our final potential energy, which would be U at point B, subtract our initial potential energy, which would be U at point A. So let's put these two ideas together. Let's write our two thoughts together. Delta U is UB minus UA, and that's equal to, I'm just going to use a little bit of distributive property here, that's equal to K times Q times QO over RB minus K times Q times QO over RA. So this is UB, this is UB, this is UA, this is UA. From this, we can conclude that our expression for electric potential energy is equal to K times Q times QO divided by R. Some important things to point out here are we include the sign of the charge. R stands for the distance between the charges. And our potential energy can be positive if both these guys are positive or if they're both negative, or our potential energy could be negative. If one is positive and the other is negative, then potential energy can be negative. So that's another important point. So U can be positive. If our U is positive, then that means that the charges would tend to separate if they were released from rest. Our U can also be negative. That means that our charges would tend to come together if they were released from rest. Okay, so the sign of the potential energy gives us an indication of how the charges would move if they were released from rest. Because we're physicists, why don't we go ahead and plot our potential energy as a function of the separation and identify what the behavior is like when we're far away or if we're close together. In our graph of electric potential energy, let's first think about what happens if the charges have the same sign. So what if they're both positive or what if they're both negative? If we look at our expression for potential energy, if they have the same sign, then our potential energy is positive. Okay, what about our behavior? So overall, potential energy goes as 1 over the distance between them. Be careful here, electric field and electric force are both 1 over r squared. Potential energy is 1 over r. Try not to get them mixed up. So if r is very small, it means that U is big. And if r is big, then U is small. Okay, so for points on a graph, if r is very small, so if our r is down around here somewhere, then our U is very big. It's up around here somewhere. So right about here. And if our r is big, so r is all the way out here, then our U is very small. U is about here. And then as a graph, that would look something like this. And in the middle, U goes as 1 over r. Okay, if our charges are opposite signed, so plus and minus or minus and plus, then our potential energy is going to be negative, and U still depends on R, so we're still going to get this same behavior. If R is small, then U is going to be a big negative number. If R is big, then U is going to be a small negative number. So if R is small, U will be down here somewhere. If R is big, U will be out here somewhere. And U still goes as 1 over r. So this is what the graph of the potential energy as a function of separation of the charges would look like.